Hello everyone, I'm Suzheng from Fudan University. It is my pleasure to introduce my work about FPGA design space exploration. My paper is called GRAEBO FPGA General Routing Architecture Exploration via Bayesian Optimization. This page shows the content of my presentation. First, we introduce our work and its background. Next, we introduce the general routing block and its design space exploration. Then, we describe our algorithm based on Bayesian optimization. Finally, we show some experimental results. In academic research, we usually use Iceland-style FPGA. These type of FPGA contain logic blocks surrounded by connection boxes and switch boxes. And the logic blocks are also surrounded by vertical and horizontal routing channels. This model has limited design space, so we have limited space to tune the performance of this model. Recently, we have many advanced features of FPGA interconnects. For example, the bent wire, which connects the horizontal routing wire and the vertical routing wire directly. And two-level muxes uses two layers of muxes to connect the pins. And there are also feedback connections, neighbor connections, and so on. So we need an interconnect model that supports advanced features and provide a huge design space. We choose the general routing block model, which can support the features mentioned above and has a huge design space. And in this work, we use Bayesian optimization to explore the design space of GRB. The GRB model contains the input connection box, the output connection box, and the general switch box. The ICB connects the routing channels to the LB inputs. The OCB connects the LB outputs to the routing channels. The GSB connects the ICB, OCB, and also routing channels together, and it also supports feedback connections and neighbor connections. The routing channels support band patterns. So the GRB model have a very huge search space because we can tune the connection relationships between ICB, OCB, routing channels, and we can also tune the routing wires. The huge search space poses a great challenge to our DSE algorithm. In this work, we model our problem as a black box optimization problem. We generate a GRB model and put it into a tool based on VPR. Then we get the area and delay of the GRB model. So the black box is the area and delay of a GRB architecture evaluated by VPR. This page shows the objective function in our optimization process. In this work, we minimize the area and delay obtained by a GRB architecture. Our algorithm is based on Bayesian optimization. Bayesian optimization contains a surrogate model and an acquisition function. The surrogate model tries to model the black box. In this problem, the surrogate model tries to model the process conducted by VPR. The acquisition function try to sample a new point based on the current knowledge. And it can balance exploitation and exploration. Exploitation means to get a good result based on the current knowledge, and exploration means to search an unknown area. In Bayesian optimization, we use Gaussian process, which can output the mean value and a variance. So we can use the mean value as a prediction of the performance and use the variance as the uncertainty of our prediction. To utilize a low mean means exploitation, and to utilize a high variance means exploration. However, typical Bayesian optimization has a problem. It is slow with high dimensionality and many iterations. Unfortunately, our GRB model has 371 parameters, and so we need more than 1,000 iterations to get a good result. The tree-pattern estimator method tries to substitute the Gaussian process with a mix of Gaussian model, and finally it gets an acquisition function that is more efficient, and so it achieves faster computation than a typical Bayesian optimization. To utilize Bayesian optimization, we need to parameterize the GRB model. The GRB model has two types of parameters. First is the segment distribution. We need to specify the number of different wire types. And also, we need to specify the positions and directions of the band patterns. The second type of parameters is the driving relationships. The GRB can connect running channels, logic blocks, ICB and OCB, so we need to specify their relationships. Our algorithm is quite simple, following a sequential model-based optimization scheme. In each iteration, we obtain a new GRB parameter with EI, evaluate the parameter on VPR, and then we update the surrogate model with our evaluation results. This page shows the results and compare our results to others. GRAEBO achieves up to 25% improvement of area and up to 20% improvement of delay. In terms of area delay product, GRAEBO achieves an improvement of 38. This result is significantly better than the GRB model searched by a simulated annealing algorithm. And they are also better than a CBSB model. This page shows the detailed comparisons of GRAEBO and the GRB searched by simulated annealing and also the CBSB FPGA model. In most cases, GRAEBO achieves better performance than the GRB searched by simulated annealing, and simulated annealing achieves a better performance than the CBSB. That's all. Thank you.